Algebra 2, section 11.3, we're talking about geometric sequences. This is a different type of sequence from the arithmetic one. It's still a list of ordered numbers, but this time we're talking about multiplication instead of addition. So you can see that we're multiplying by a particular value here, and when we talk about multiplication, we talk about a constant ratio. You can find that ratio by taking any term and dividing by the previous term. In this case, if we take the terms in this particular sequence and divide them, 6 divided by 2, 18 divided by 6, 54 divided by 18, every time we come up with 3. So we know that the constant multiplier for this one is 3. Therefore, we can determine other terms of the sequence, whether it be the next term or whether it be the 500th term or something like that. So there's an example in the book that they talk about, is this sequence geometric? And if it is, then what's the ratio? So we're taking a look at this particular example. We talk about 15 divided by 5, that's 3. 45 divided by 15, that is also 3. And 135, divided by 45. That also ends up being 3. Every time we took the term divided by its previous term, we got 3. So that must mean that yes, it is indeed geometric, and that the R value is that number 3. We'll try again. 30 divided by 15 is 2. 45 divided by 30 is not 2. Right there we can see that we have a problem. So when I did this, I got 2, but when I did the next one, I did not get 2. Now, doesn't matter that it's 1.5. Could have been anything. The important thing is it's not 2. So this is not geometric. If you look at it, you can also see that you're adding 15 each time. That's arithmetic. Now, the geometric also has a recursive and explicit. Sorry for a couple mistakes that I made when I was writing up the notes. The recursive one starts out with a first term, so it has a number to begin with. Remember, the recursive ones always have two parts. The first starting point, and then how to find the next term. So you can see what I'm doing here. It says that the next term is equal to the ratio R times the previous term. So for instance, this example that we were doing right a few minutes ago, let's say the one we started with at the beginning of the lesson, 2, 6, 18, 54. Its first term was a 2. The next term was the ratio, which we found out was 3, times the previous term. That is your formula. That's your recursive formula. And if you gave me this and asked me to duplicate the terms of the sequence, then I would know to start with 2, and then triple it, triple it, triple it. That's all that recursive formula is telling me to do. Now, would I like that to be the one I use to find the 500th term? No, that is not what I would use. Besides, I think that the 500th term would be rather large in this case. So I'm not even going to find the 500th term. Maybe the 50th term. Let's go with the 50th term. I still would use the explicit formula, which says that the next term is equal to the previous, or the first term. The first term here was 2, times the ratio to the n minus 1 power. So, how about this? 2 times 3 to the 50 minus 1 power. Since I know that 50 minus 1 is 49, I'm just going to use 49. Still a rather large number. 4.79 times 10 to the 23rd. Kind of big. Well, here's another example. Anytime you are multiplying by a percentage, or anytime you're talking about increasing or decreasing by a percentage, you know that's multiplication. That's what we talked about in Chapter 8, the exponential growth and decay models. This one would be decay. Why? Because we are multiplying by something smaller than 1. So the length starts out at 10. So if I'm going to write the explicit formula, I got G sub n equals the first term times the multiplier to the n minus 1 power. Find the length after 5 reductions. Well, just plug in if we're looking for the sum after 5 reductions. Now wait a second, is this the 5th term or the 6th term? If the first term is a 10, we want 5 reductions. We're not looking for G sub 5, we're looking for the 6th term in the list. And the 6th term in the list would be 10 times 0.64 to the 6 minus 1. Sorry for the yawn. My apologies. Too much work. Whoops. 6 minus 1 is 5, so that's why I'm only going to raise it to the 5th power. Well, no wonder it was so blurry. Much better. Sorry, I had to get my my hydraulic lift in the back on the calculator. If you don't have me in class, that kind of probably won't make any sense. But that's okay. It'll be a lot more clearly seen on the calculator now. Alright, so let's see here. We've got 1.074, excuse me. Now the geometric mean, different from the arithmetic mean. The geometric mean is multiplying two numbers together and taking a square root instead of adding and dividing. So that geometric mean is a whole lot different than what you're used to. So for instance, if you had 3 terms and you were missing the one in the middle, but you had the first and the last, you could use the geometric mean to find the one in the middle by multiplying the 2 and the 18 together and taking the square root. So the missing term there was 6. What would you do in a case where you had 5 numbers and 3 of them were missing? Well, you're going to find the geometric mean of these two. So 3 times 48, take the square root. What do we got there? 3 times 48 is 144. So that's the square root of 144, which is 12. So we know that value is a 12. What are we going to do here? Probably the same thing. 3 times 12, take the square root. Gives me 6. Twelve times 48, take the square root. Now by this time you should probably already see that the multiplier is 2. Therefore you could take 2 times 12 and get 24. So I already know that this answer is going to be 24, but, you know, just for argument's sake, 12 times 48, square root of 576. And the square root of 576 is indeed 24. So, I knew it already, but just so I'm showing the work. And looking at the smiling face. Alright, see you in class.